Hey guys, Assalamualaikum. Welcome back to another virtual lecture. In today's video, we're going to learn about hypothesis testing for two samples. Now before that, let me do a little bit of recap. Here's a summary of what we've learned so far. Now before this, we've conducted hypothesis testing to test whether or not a particular population mean is equals to or greater than or lesser than a particular hypothetical value. That is why for step 1, we wrote this way, right? Mu is equals to something versus the alternate mu is not equals to that same something. And of course, this sign can either be greater than or lesser than, all right? So what we basically have done before was we've only focused on one sample. Now, of course, these tests can either be in the cases of when we know the population standard deviation. So normally when we know the population standard deviation, the case is also where we have a large sample size. So this is the case where we used Z as our test statistic. And then there's also the case that when we don't know the population standard deviation. Okay, and that is also normally the case when we have a small sample size. And here is when we use the T as our test statistic. So today we're going to continue our study on hypothesis testing by testing population mean but for two samples. Now when we talk about two samples, it can either be independent from one another or the two samples can be dependent on each other. Let's try to understand the basic purpose or objective of a two population means test. Okay, so now here we've got two populations, right? Population 1 and population 2. From this population, if it's possible, we can get the population mean. So we have population mean 1 and population mean 2. Now, in an ideal situation, it would be very simple just to compare between the two, right? But we've learned from the previous topic that it's impossible, very difficult to get information from everyone or everything in that population. That is why we collect a sample. So here's a sample from population 1, and here's a sample from population 2. Now from these samples, we can get what we call the sample mean from the first sample, and here we can get the sample mean from the second sample, right? For a hypothesis, you have to understand, you have to remember that we're actually interested to test these two. But because it's impossible to get information on them, we use their best estimate, which are the sample means. Okay, so effectively in step 3 of hypothesis testing, we are comparing between these two guys. But once we get the result, we will generalize it back to the population. Now from this very simple illustration, okay, it's actually important to understand this because it will guide your understanding to writing the hypothesis. Okay, remember we've got 6 steps, right? We've got 6 steps in the hypothesis testing. Now the 6 steps are the same regardless whether it's a 1 sample test or a 2 sample test, it's the same steps. Step 1 is always writing the hypothesis. Step 2 is writing down our alpha. Step 3 is calculating the test statistic. Step 4 is writing down the rejection rule. Step 5 is making the conclusion. And step 6, interpretation. So all of the 6 steps are the same. But there are 2 differences, okay? One difference is how we write step 1. Okay, because of course, step 1 is literally telling us what the objective of the test, what's the test all about. So of course, there's another difference is in calculating the test statistic in step 3. Okay, let's look at step 1 first. Now, if it's a 1 sample test, it's very simple because, okay, look here. Let's imagine that this is closed, okay? For a 1 sample test, you only have 1 population. Therefore, we only have 1 sample and we only have 1 X bar. That is why, how do we write the hypothesis for a 1 sample mean test? Null is mu equals to a particular or a hypothetical value, let's say 10. Okay, so this mu is basically the population mean from that 1 population. Okay, so we want to test whether that mu is equivalent to some value, okay, against the alternate, which is not equals to that value. Or it could be more than that value or less than. Okay, so remember, the sign here depends on the question, all right? But if it's a 2 sample mean test, okay, let me just have a divider here. Okay, again, this is step 1, but for a 2 sample mean test, okay, how do we write the null? Okay, this time around, okay, as you can see here, we've got 2 mu's, right? So if before we assume that mu equals to 10, because remember, that's the definition of null hypothesis, right? Is what we assume to be true. So we assumed mu equals to 10. So in this case, for the null hypothesis for a 2-sample test, we assume that these two are equals to each other. That is why we write it as mu1 equals to mu2. Are they really, equals to one another? We don't know. That is why we have to do the test. So what about the alternate? The alternate here, well, similar this way. It could either be that both population means are not equals to each other, or one population mean is greater than the other, or one population mean is smaller than the other. Again, whatever the sign we write here depends on the question. Okay, so I hope you can see the difference in writing the hypothesis for a 1-sample and a 2-sample population mean test. Now, as mentioned, the other difference lies in step 3. Okay, step 3 is calculating the test statistic, right? Test statistic. Okay, so it depends on several factors. 2, actually. One is if we know the population standard deviation and if the sample size is large. In that case, we use the Z as the test statistic for a 1-sample test. Okay, so how do we calculate that? X bar minus mu over sigma over the the square root of n. And if we have a large sample size, but if we don't know what the sigma is, it's okay, we can just substitute it with S. Okay? Or if we have a small sample size and we don't know sigma, we use T. All right? So it's X bar minus mu over S over the square root of n. Okay, so these are basically the test statistic for a 1-sample population mean test. In the case of 2 samples, if both samples are large, okay, we use Z. But if both samples are small, it's another test, okay, which we will learn in another video. Okay, so today we're just going to focus on the case where both N1 and N2 are large. Okay, and large, normally we have the population standard deviation. Remember, the assumptions is that both of these populations follow the normal distribution. Okay, the 2 samples here are independent of each other, and then the standard deviation for both the populations are known. Okay, now that's our assumptions here. So with those assumptions, we use Z as the test statistic. So how do we write the test statistic for a 2-sample population mean test? Now let's look at the numerator here. Here we only had 1 X bar. Why? Because it was only 1 sample, right? But now we have 2 sample means. So up here, we just find the difference between the 2 samples. Okay, remember? Okay, let me just refresh. Remember, the objective of this test is we want to see whether there's a difference between mu1 and mu2, where we can correspondingly find the difference between these 2 sample means, okay? So that is why here we find the difference between X bar 1 and X bar 2. Okay, see the difference? Right, over, now down here, okay, if you look, let's take this guy, put it separately. Sigma, okay, another way to write the sigma, okay, is actually, sigma is the square root of variance, right? Okay, so here's variance over sample size. Now, if we square root both the numerator and the denominator, what we get is sigma over square root of n. Correct? Okay, so now take this fella, put it here, because now we've got 2 samples. We've got 2 of everything. So here we've got the first variance over the first sample plus, okay, the second variance over the second sample. Now, because it's a standard error, we have to square root it. Okay, so basically this is the formula to find the test statistic for a 2-sample population mean test, assuming that sample sizes are large, and we assume that both population standard deviations are known. Okay? Now let's take a look at this example. Hopefully we'll be able to illustrate a 2-sample population mean test better. Okay? As part of a study of corporate employees, the top management of IIUM wants to compare the distance traveled to work by employees at its branches at Gombak, with the distance for those in Kuantan. A sample of 35 Gombak employees showed that they traveled an average of 370 kilometers a month. A sample of 40 Kuantan employees showed that they traveled an average of 380 kilometers per month. The population standard deviation for the Gombak and Kuantan employees are 30 and 26 kilometers respectively. At the 5% significance level, is there a difference in the mean number of kilometers traveled per month between the Gombak and Kuantan employees? Now, first things first, let's identify all of the information given. Okay? Since we have two samples here, it is very, very much encouraged to define the random variables. Otherwise, you might get confused. Okay? So here, let me just denote. Let's G, okay, be all of the things or information for the Gombak branch, okay, and K for Kuantan. Meaning it can be NG, NK for the sample sizes. It can be X bar G, X bar K, and it can be sigma G and sigma K. Okay, but if you prefer to do a 1 and a 2, it's fine. You can put here 1 for Gombak, 2 for Kuantan, not a problem. All right, so what do we have? The sample size for the Gombak campus is 35. Okay, the sample for the Kuantan is 40. The sample mean for Gombak is 370 kilometers. The sample mean for Kuantan is 380 kilometers. The population standard deviation, okay, see now we know the population standard deviation is given, all right? So hint, we're using a Z later. G is 30 kilometers, and the population standard deviation for Kuantan is 26. Okay, so write down everything, put it aside. Okay, for step 1, as I've showed you just now, the null hypothesis is we always assume that both population means are equal. Yeah, so we assume here for the null hypothesis, we assume that the average kilometers traveled by Gombak workers is exactly equal with the average kilometers traveled by the Kuantan workers. Okay, but from the question here, because we were testing whether there's a difference between them or not, that is why this is our alternate. Now, step 2 is basically to determine our level of significance, and it's given alpha is 5%, so 0.05. Is this a one-tailed or a two-tailed? Yes, this is a two-tailed test because the sign for the alternate hypothesis does not specify any particular direction. Not equals to can either be more than or less than. Okay? Next is step 3. Okay, meaning we need to calculate our test statistic. Now, from the case, from our story here, we know that the sample sizes are large. One is 35 and the other is 40. And then we know the populations and deviations for both. So it's a clear-cut case where we should use the Z as the test statistic. So remember the formula just now? At the numerator up here, we find the difference, yeah? The difference between the sample mean for Gombak minus the sample mean for Kuantan, okay, over the variance, okay, the variance for Gombak over the sample size of Gombak plus variance for Kuantan over the sample size for Kuantan. And because it's standard error, we have to square root it. So we just plug in all the figures that we've identified earlier. So up here is 370 minus 380 over, okay, what they gave us just now was standard deviation. So make sure to square it, yeah, because here is variance, over 35 plus 26, square it over 40. Square root this. So I'll give you time. Why don't you pause the video for a while and calculate that. Okay, once you solve this, you will get a minus 1.53. Okay, so this is the test statistic for this particular case. The next step is step 4, which is we want to write down what our rejection rule is, and as always, we want to sketch and show the rejection area as well as the acceptance area. Now, we've identified that we use the Z distribution, right, as the test statistic. So here would be our Z. Now, here in the center, here is also 0. Now, the reason is that, okay, let's take a look here. Let's go back to our step 1. Here we hypothesized that there is no difference between the population means for the Gombak and Kuantan campus, right? So there's no difference. So in other words, if we were to, take this mu k and put it to the left-hand side, how would it look like? It would be like mu g minus mu k. And because there's no difference, it will be 0, correct? Same likewise here. Okay, if let's say we were to take the right-hand side and shift it to the left-hand side, okay, it will not be 0. Okay, some textbooks write the hypothesis this way. Okay, it's just that our textbook write it this way. Okay, why is this important? I want you to see here, this 0 is represented here. Okay, now, we know that this is a two-tailed test, correct? From here is a two-tailed test, meaning we've got 2 rejection areas. Okay, so this is where we write reject the null. Here also is where we write reject the null. And since it's a two-tailed test, we've got 2 rejection areas, therefore our alpha is divided into two parts. Okay, so here alpha is basically 2.5% or 0.025. Alpha is 0.025. And here's our acceptance area, so we write it as do not reject the null. Okay, so since we've got 2 rejection areas, therefore we will have 2 critical values. So if you remembered, this is a two-tailed test. Alpha is 5%, so if you recall how we did it, this is a shortcut. It's basically plus minus 1.96. So you can refer to the previous videos on how we get this shortcut. So now that we have our critical values and we have the basic sketching of our rejection areas, we need to write down the rejection rule. So what's the rejection rule? It's basically we're just, explaining what we drew. So here we want to reject the null if the test statistic is greater than 1.96 or if the test statistic is less than minus 1.96. Okay, so these 2 are our rejection rules. Next is step 5 and 6. We can put it together. So we want to compare where our test statistic, okay, is compared to the rejection or acceptance area. So we can see minus 1.53 lies here, guys. Okay, minus 1.53 falls in the acceptance area. So what we do is we need to not reject the null hypothesis. So we can put it here, since the test statistic lies in the acceptance area. Okay, what do we do? We do not reject. So we put it here. We do not reject the null hypothesis. Okay, so you can underline that. And what do we conclude? And we can conclude that, okay, to conclude, let's go back to the first step. Okay, you can see here. So we're saying that we do not reject. So if we do not reject, we're accepting it, we're taking it. So what do we say? Is there any difference? No, there is no difference. So meaning that we need to, adjust or paraphrase the question. Okay, so we can't say there is a difference. We have to say there is no difference, okay? So here, let's go back here. We can conclude that there's no difference. Oops, I just realized you can't see me. Okay, there is no difference in the mean number of kilometers traveled per month between employees, okay, you can write info, between employees in Gombak and Kuantan. Okay, maybe we can underline that. Do not reject, and there's no difference. Okay, highlight your answers. Okay, what if they ask you to find the p-value? Okay, so remember how to find p-value for a z distribution? It's half minus the probability of our test statistic. So our test statistic was 1.53. So why don't you look at your z table? Look at 1.53. You will get 0.4370. Okay, so half minus 0.4370. And remember, because it's a two-tailed test, whatever the result here, we want to times 2. So we will get 0.126. So as you can see here, since the p-value, which is 12.6%, is greater, yeah, is greater than the alpha, which was 5%, we can see that we don't have evidence that the null is false, therefore we do not reject the null. As you can see, okay, do not reject the null. So as you can see, the result that we get using the p-value method is similar to the result that we get using the 6 steps hypothesis testing method.